Let's talk about this example. We left off at the very end, ran out of time, but I encourage you all to work on this on your own, and I don't know if you got to it last time, but let's go through it. So this was the last example of the L'Hopital's rule, and this is one of those ones where it looks like a product, and you have to change it into a quotient somehow. I'm going to say, first of all, we got to look at what happens if you just try to plug in. Now, in this case, plug in, you're not really allowed to plug in infinity. But so what I'm going to write here is somewhat informal, but really what it looks like is something like infinity squared times sine of 1 over infinity. Now, you have to interpret what these things are. Of course, infinity is not a number, so you can't treat it just like a number. But anyway, infinity squared is basically infinity. And then I have sine of. What do you think about 1 over infinity? How can I interpret that?
That's like approaching 0.
Yeah, that's basically 0. So I'm just going to, for the purposes of plugging things in, it amounts to sine of 0. And sine of 0 is 0. So this is looking like infinity times 0. And this is an indeterminate form, right? When you see infinity times 0, that means you can use L'Hopital's rule. If we had gotten infinity times infinity, then we just say that's infinity and the limit does not exist. Or if we'd gotten 0 times 0, then that's 0 and the limit equals 0. But infinity times 0, that is indeterminate, and we can use L'Hopital's rule. And so what we have to do is force this to look like a quotient. And I'm going to do this way. I'll put sine of 1 over x up there and just 1 over x squared, I guess, down here.
How do you convert that to 1 over x squared from x squared?
Because it's in a denominator now.
Oh, okay.
So really it's sort of 1 over x squared. Yeah. The other way you could have written this as a fraction would have been like x squared over 1 over sine of 1 over x. But in my opinion, that's a little more complicated to work with. So I prefer the first way that I did. Although either way, in theory, would work. Remember, I'm about to do L'Hopital's rule, which involves taking the derivative on the top and on the bottom. And so what I wrote there in black seems easier to me to handle than the blue one there. So it's not wrong. You could have done it that way, but it's going to be easier to do it this way that I did. So now I'm going to do the L'Hopital rule. So we take the derivative on the top and on the bottom. Of course, the bottom, and it's still going to be lim x goes to infinity. The bottom, 1 over x squared, that's the same as x to the minus 2. And so the derivative of that is negative 2x to the negative 3, right? That's the derivative on the bottom. On the top is going to be a little more taxing. We'll have to do the chain rule because this is the sine of some stuff. And so when I take the derivative, the chain rule says, first of all, the sine becomes a cosine. That's the derivative of the outside part. Same thing on the inside. Then times the derivative of the inside. Derivative of the inside, 1 over x is x to the minus 1. And so the derivative of that is negative x to the minus 2. So this is what we get after taking the derivative on the top and on the bottom. All right. How am I doing so far? Let's try and simplify as much as we can. I'm going to plug in the infinity again, but we might as well try and simplify. We have powers of x which can cancel out. X to the minus 2 up top, x to the minus 3 downstairs. Is this confusing to anybody else? Yeah. Okay. Thank you for that. Maybe would you mind if I just so that I don't confuse myself too much? I'm gonna flip all the powers around. So when I see x to the minus 3 on the bottom, that's the same as x to the plus 3 on the top, right? And then when I see x to the minus 2 on the top, that's the same as x squared on the bottom. And then I also have a constant. I have 2 minus signs which are going to cancel. And I have a 2 in the denominator, so I'll just keep the 2 in the denominator. I think that's the same. Yes? Because there used to be a 2 over here.
Does that 2 have to go off with that x width, or?
No, because, all right. Because this negative exponent is on the x, right? It doesn't apply to the 2, though. The 2 is in the denominator. It's not to any other negative power, so it stays in the denominator. If you like, you could factor this all the way out and put a 1/2 out here. Forget about the 2 in the denominator. Sorry, I hope the folks at home can see all right. I just got something weird just happened on my computer. All right. Okay, now I think it's clear how the x's will cancel out, right? X squared in the denominator cancels, and we end up with just one x on top. So it's lim x goes to infinity, cosine 1 over x times x, right? Over 2. The over 2 doesn't matter too much. I suppose it does matter, but it's not going to cause us any problems, really. All right? What? I put infinity. I meant x, right? Although, I mean, in the next step, I'm going to plug in the infinity, so to speak. All right? Okay, let's do it. So we're going to try to plug in again. Maybe I'm going to have to do L'Hopital's rule again, or maybe I'll just get the answer at this point. Try to plug it in again. So I get cosine 1 over infinity times infinity. I put this little arrow here rather than an equal sign because what I'm writing over here is not really, this is not very formally precise. Of course, there's no such thing as 1 over infinity or whatever, but I hope everybody knows what I mean. Come on, my pen is... Okay, and this cosine 1 over infinity, I can write as cosine of 0 times infinity over 2. This is 1 times infinity over 2. What's your interpretation of that? Do I need to do L'Hopital's rule again, or can we stop at this point? Anybody have... Folks at home can shout out too if you want.
So it's 1 times infinity over 2, because cosine of 0 is 1. Take that back another step. 1 over infinity is approaching 0, and it's getting infinitely close to 0, and so that's why that is technically representative of 0.
Yeah, this 1 over infinity becomes a 0, right? Because you're thinking about what happens when I have 1 divided by some increasingly large number. It becomes 0. I would say 1 over 2 times infinity, that's basically still infinity, right? What you're really saying here is if something here is becoming very, very large, then what happens to 1 times that thing divided by 2? The answer is it also becomes very large. This, by sort of rules of simplifying infinities, this is also infinity. And so we say the limit is infinity, right? Or you could say the limit does not exist. You don't have to use L'Hopital's rule again, though. L'Hopital's rule is only when you have 0 times infinity. But 1/2 times infinity is what we have here. That's just infinite. It's not it's not an indeterminate form. And so my conclusion is the limit is infinity, right? This is a little weird, all of this talking about plugging in infinities. But I hope you did that kind of stuff to some extent in your Calc 1 class. Any questions about that? All right, so this was just finishing up one last example from last time, and now I want to go on to something completely different, if that's all right with everybody. This is the beginning of the next section, actually. The next chapter, I mean. This was the end of the L'Hopital's rule, was the end of the previous chapter. The next topic is something which I have alluded to a few times. It's a new trick for doing integrals. It's called integration by parts. This is something maybe some of you saw before. I don't know. Integration by parts. It's another kind of major trick for doing the integral. So far, we haven't done much in the way of tricks for doing the integral. Basically, we have the u substitution, and sort of that's it. But integration by parts is another general purpose trick which can sometimes work to do weird integrals. So it's a trick that's like vaguely, I would say, similar to u substitution. It involves choosing parts of the integral and calling them u. Actually, in integration by parts, you choose two separate parts, and we're going to call one the u and one the v. So you choose parts of the integral. To call them u and v, and then you use some kind of formula. And then hopefully obtaining a simpler integral. In the case of the u substitution, you try to replace everything, like instead of x's, you decide what u is going to be, and then you try to rewrite everything in terms of u, and hopefully after you rewrite everything, you get an integral which is easier to do. That's the theory behind the u substitution. Integration by parts is a similar kind of trick about rewriting the integral into hopefully a simpler form. The u substitution is based on the chain rule, and that's why the general rule of thumb is in a u substitution you always choose the u to be the inside of something, and you have the outside and the inside, and what makes the u substitution work is the chain rule, which is about the outsides and the insides. Integration by parts is based instead on the product rule. It's based on the product rule. So integration by parts is not used for something inside and something on the outside. It's used instead for a product of things inside the integral. All right? And let me just write the product rule again in a, well, if I were writing it like this, can I just use sort of primes instead of d dx?
Professor, is this one simplifies it like dv?
Yeah, right. It's that thing, which you may have heard of. It sounds like you have heard of. The product rule says if you have u times v and you do the prime of that, what you get is the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing, like that. Right? That's the product rule. Everybody knows the product rule. If I write this instead of with the primes, I'm going to write it in a slightly more suggestive way. Which is a d, usually we don't use d's in this way, but I'm going to write it. So d means derivatives here. I'm writing it that way because now you can put integral signs everywhere. So take the antiderivative through the whole thing. If you integrate, take the antiderivative everywhere. What you get on the left is just uv, right? Because I had the derivative of uv on the left side. But if I take the integral, that will undo the derivative, the antiderivative of the derivative. They would cancel out, and I just end up with uv. On the right-hand side, what I get is integral u dv plus integral v du. And this is basically the integration by parts formula, although we usually solve it for integral u dv. So if I solve this for integral u dv, it says uv minus integral v du. And this is the integration by parts formula, which you definitely need to memorize, although we're going to do it so often that hopefully you will just naturally remember it. The integral of u dv is uv minus integral of v du. Make sure you put the integral signs in the right place. This is the integration by parts formula. All right? So the way you use this is, what you start with is the thing on the left side. So we look at the integral. And you have to break it into these two parts. So you choose part to be u, and then the rest of it to be dv. All right, and they have to be multiplied together inside the integral. The left-hand side of the integration by parts formula is u times dv. So you have to choose part of your integral to be the u, and the other part to be the dv. And then you compute, then you find du by taking the derivative of u as usual, just like in the u substitution. This is the derivative of u. And you also find v, and this will be the antiderivative of dv, right? See, in your integral that you start with, you choose part of it to be u and part of it to be dv. In order to plug into the right-hand side, you need to know what du is right here, and you also need to know what v is right here. Du is the derivative of u. V is the antiderivative of whatever you chose to be the dv. All right? So you choose your two parts, then you find the du and you find the v, and then I'll just say plug into the formula. And do the new integral, right? The formula involves another integral on the right-hand side. So you end up with another integral which you have to do. Hopefully, if you did everything correctly, your new integral will be easier to do than what you started with. So I'm going to say plug in the box and do the new integral. So let's try some examples. I'm going to start with a simple one. This is the classic example of integration by parts. Integral of x e to the x dx. The classic. We begin by choosing the two parts. All right, now we're going to talk in a moment about sort of basic strategies for how you decide which part should be which. But I have basically two things here, the x and the e to the x. One of them I'm going to choose to be the u. The other I'm going to choose to be the dv. And I'm going to pick, just because I know how this is going to work out, I'm going to choose u to be x and dv to be e to the x dx. Because of the way you do this, the dv should always include the dx part. But there's some choice that you have to where you're going to put everything else. But like I said, because I know how this one is going to work out, I'm going to choose it this way. If u is x, then what's the du? You take the derivative of u. So the derivative of x being 1. The du is just dx, just like in the u substitution. Du always includes dx. And dv always includes dx. This one, how do we get v? It is the antiderivative of dv. In this case, will be the antiderivative of what I chose for the dv, which is e to the x, and the antiderivative of that is e to the x. All right. Ordinarily, we would put plus c here, but actually, the plus c you don't have to worry about it in the middle of your integration by parts. It turns out you can just put the plus c at the end of the problem, and everything will be fine. All right. We're doing all right so far? Okay, and now I'm going to plug all of this into the integration by parts formula. So I go uv minus integral v du, right? This is the integration by parts formula. And it equals u is x, v is e to the x, minus integral, v is e to the x, du is dx, like that. So this is what I get from the integration by parts formula. X e to the x minus integral e to the x dx. All right, we're almost done. We're not quite done because there's still an integral remaining to do. This is what I meant when I said plug into the box and do the new integral, right? This is the new integral. Hopefully, the new integral is simpler than what you started with originally. And in this case, it is, because we can do the integral of e to the x. What is the integral of e to the x? It is e to the x. Great. And then finally, I'll put my plus c there. And this is it. Anybody got any questions about that? This was a simple integration by parts example. All right.
Why? I mean, this is kind of a dumb question, probably, but why are you reinserting that dx? Does that have to do, like, in your step where it's uv minus integral v du?
Yep.
On the right side of that equation where you have e to the x dx, I know you have that dx from above, but shouldn't you be bringing down du?
Yes. Yeah, exactly. But up here we already said du equals dx.
Oh, it's one dx. Okay.
Yeah, so that's why it's dx here.
All right, makes sense.
Yeah,
And
that's,
if that dx represents a number, like let's say du is like 1/2 dx or something like
Yep.
that, then you just bring that down to
yeah, then that would have got stuck into that integral. Yeah, yeah. So these parts here, this is the u, this is the v, this is the v, and this is the du, right? Yeah, we just plugged it all in. All right, let's talk a little bit in general about how you should choose the various parts, right? In the u substitution, everybody knows you choose like the u to be the inside of something. How about in the integration by parts? So just like in u substitution, there's not like a hard and fast rule. You have to, at some level, just choose whatever works. But here's the general principle. General strategy for choosing the u's and the v's. Remember, u is what you start with, and you end up replacing it with du's. So we generally want to choose u to be something that I like to differentiate. That means take the derivative of. Something I like to differentiate. That is something which maybe becomes simpler when you take the derivative of it. I'm thinking of something like a polynomial. Because when you take the derivative of a polynomial, it becomes simpler, right? It becomes a polynomial of lesser degree, or maybe it becomes a constant. That's why in that example that you just saw, I chose u to be x, because du becomes 1 dx, which is simpler. Or you could sometimes choose something like e to the x to be the u. It doesn't get simpler, but at least it pretty much stays the same, right? Maybe sine or cosine will work for the u, because these also don't get simpler, but at least they more or less stay the same. So those sometimes are good choices for the u. And also natural log of x is sometimes a good choice for the u, because the natural log will turn into 1 over x, which is different, but usually 1 over x is easier to deal with than the natural log, right? So the general idea is you choose something which gets simpler after you take the derivative, all right? Whereas the dv, you want to choose something which gets simpler when you take the antiderivative. That's because that's what you have to do to turn dv into v. So you choose dv to be something I like to integrate.
Professor, let me ask you a question.
Sure.
So let's say you're doing the same problem and I pick a different u than you do, and can you still work the problem out no matter what you pick that u to be? Like, theoretically, it would be harder to derive certain things in a function, but could you do it anyway
Yeah.
and get the same answer, or would it be a different answer?
In theory, you could do it any way you like and get correct answers, although if you choose it wrong, you will see, actually in most of the examples that we do, there's only one right way to do it. And I'll show an example what happens when you choose them the wrong way around. Okay, anyway, let me just finish what I was saying here. You choose the dv to be something that you like to integrate. So something that maybe stays the same when you take the integral, or perhaps gets simpler, although if you think about it, there aren't many things that get simpler when you take the integrals. But there are some things which at least don't get more complicated. So something like e to the x, sine and cosine would be good choices for this. Maybe a polynomial, although polynomials will typically get more, the degree will increase when you take their integral. So I would say sometimes polynomial. Not ln of x, though, because the natural log of x does not have a nice integral formula. That its derivative is nice, 1 over x, but the integral of the natural log of x is actually something we've never talked about, because it doesn't have a particularly nice formula for it. All right, these are the general strategies. Let's try another example. And I want to kind of demonstrate what happens when you choose things the wrong way around. But let's do it the right way around first, and then we'll try another set of choices. This is all about making good life choices. Most of the time, if you make a bad life choice, it's not the end of the world. That's how you learn. Okay, so the good life choice for this one is I'm going to choose the u to be the polynomial piece, and the dv I'm going to choose to be the rest of it, which has to be e to the x and dx. Remember, the dv should always include the dx, because the dv is the thing which I am going to try to integrate when I transform it using the integration by parts. All right, then what's the du? What can you say here? Yes, that's true. But actually, when you're doing the integration by parts, there's no need to solve it for dx. In fact, it's not helpful to solve for dx. So I'm just going to leave it like du equals 3 dx. When you do u substitution, usually you want to solve it for dx, but it's not helpful in the parts. Okay, and then v will be the integral of e to the x, which is e to the x, yeah. So the v is always the integral of the dv, which in this case makes the v equal e to the x. All right, let's plug it all into the integration by parts formula. So this is going to equal uv minus integral v du. We get u is 3x minus 2, v is e to the x, minus integral v e to the x, du is 3 dx. All right. And now we just have to do the integral on the end there. Not so hard, although I don't like the 3 in there. Let's pull the 3 out of this integral sign. So I just keep this front stuff the way it is. 3 integral e to the x dx. Often you will have to do a little simplification step here to prepare for doing that integral. And let's do it. We get 3x minus 2 e to the x minus 3 e to the x plus c. That's how it is.
When you're integrating through dx, would that be 3x dx?
No, because so in here you have e to the x times 3 dx.
Yeah.
When you have two things inside the integral multiplied together, you do not just do each integral separately, right? You have to somehow simplify it or something. And in this example, the appropriate thing to do is pull the constant out of the integral. Then we just have e to the x dx. All right. Yeah, this is somewhat upsetting. It causes me to hang my head. Here's a actually very common mistake that I see people do. They start here, they do the integration by parts formula, get to here, and then they do something like this integral becomes e to the x, and then this one becomes 3x. Because they see the 3 there, and they integrate the 3, and they get 3x. And so they say that the answer is, this stuff here minus that, all right? But everybody knows when you have things multiplied together, you cannot just do each integral separately, okay? If you really thought that was okay, you should have just done it at the very beginning. Then you didn't have to do all of this business, right? The whole point of the integration by parts is that you cannot just take two things multiplied and do the separate two integrals, all right? So don't do that. All right. Anyway, this is the answer to that integral. All right. This is a classic integration by parts. Can we just for a moment talk about what would happen if you chose things the other way around? All right. Let's see what would happen if I chose things the other way around. You don't have to write this down if you don't want to, because this is going to be wrong. Or not exactly wrong, but just it's not going to work. If I start with the same thing, but this time I'm going to pick it the other way. U equals e to the x, dv equals 3x minus 2 dx, right? We can still do all of this business. So if u is if u is e to the x, then du is e to the x dx. That's the derivative of u. If dv is 3x minus 2, v is integral of 3x minus 2 dx. And you can do that. It's 3 halves x squared minus 2x. All right? And now plug into the integration by parts formula. It becomes uv minus integral v du. And we get, okay, u is e to the x. V is this stuff. Minus integral. V is this stuff again. Times du is e to the x dx. All right? Nothing here is wrong. Like what I wrote is not incorrect. But now, the next step is to do this integral. And I ask you, how do we do this integral? The answer is, well, this integral is even worse than what I started with. All right? So at this point, you should feel like that didn't really work. Not that it's wrong, but it didn't make my integral any simpler. All right? And the whole point of the integration by parts is to start with a complicated integral and replace it with an integral which is easier to do. But this is done the opposite, right? I replace it with a harder integral. So this is harder than where we started. This suggests to you that probably you made the wrong choice at the beginning, and you should go back and make different choices. All right. Bad choices. Bad life choices, yeah. It's not incorrect, what I wrote there. It's just not going anywhere, right? Okay, let's try another one. The two examples we've done so far have both been they look kind of the same. They were like a polynomial part times the e to the x. That's not the only time in which you can do the integration by parts. How about this? Integral of 3x cosine x dx. All right. Integration by parts typically works when you have a product inside the integral. All right. I hope there's nobody out there who's secretly thinking, can't I just do 3/2 x squared and then sine x? Isn't that the answer? No, that's not the answer. You can't do that with the integral. If you have things multiplied on the inside, you cannot just do the integral of the two things separately. That is bogus. I'm going to keep it on there just to call that out. You can't do that, all right? What do you do instead? You do integration by parts instead. That's the whole point of integration by parts, is that you're not allowed to do that, which I wrote there in red. So we got to choose the u and the dv. Anyone want to make a suggestion here? I like this idea. Pick u to be 3x, because in the integration by parts, this u eventually will be replaced by du, which means the x will go away, which sounds great to me. So if u is 3x, then du is just 3 dx, right? This means dv has to be everything else, which is cosine x dx. And so v will be the integral cosine x dx. And what's the integral of cosine x? It is sine x, right? And now we can do the integration by parts formula. uv minus integral v du. I always write it down in hopes that this will help everybody memorize the formula. uv minus integral v du. It is 3x, that's the u. v is sine x minus integral v sine x times 3 dx. That's the du part. Can we do anything to simplify the integral before we do the integral? Whoa, sorry about that. Bring out the 3, yep. And this actually will usually happen. Usually there will be some extra constant stuff in there that you want to factor out. Right. And now we can do the integral. Integral of sine x is negative cosine x. And so my final answer is 3x sine x plus 3 cosine x. I turned the minus to a plus because the integral of sine is minus cosine. Plus c as always. All right. Anybody got any thoughts about that? This is the integration by parts. It works. You can always, maybe I'll say it, you can always check your answer. Check yourself before you wreck yourself. You can check yourself by taking the derivative of the final answer if you did everything correctly, you should end up with what you started with. So we can check it. Check it by taking the derivative of what I ended up with at the end. 3x sine x plus 3 cosine x. What will we get? So in 3x sine x, you have to use the product rule. This is not a surprise. The integration by parts is based on the product rule. So if you are checking your answer and you did integration by parts, it will always result in doing a product rule. So I go the first thing times the derivative of the second thing plus the second thing, sine x, times the derivative of the first thing, which is 3. And then plus the derivative of 3 cosine x is negative 3 sine x. And what happens? This guy cancels this guy, and I end up with 3x cosine x. And this really was the thing on the inside of the integral that I started with. This checks out. It checks out because this here matches with this, right? Which is what I wanted. This is how you know you did it right. All right. I got one more thing to say, and then I have some for you all to try. I have one for you all to try. Oh no, actually. Got my papers backwards here. Okay. I have one more example, and then I have some for you all to try. Very strange example. Sometimes we can choose the dv to just be dx. This is a weird integration by parts. Usually this doesn't work very well, but in this way you can actually take the integral of the natural log. This is something I said earlier today. We don't have a nice formula for the integral of ln of x, but it turns out you can do this using the integration by parts, where one of your parts is just dx. So I'm going to choose the u to be ln x and the dv to be just dx. All right? Uh-huh. Yeah, you can think of this as 1 times dx if you want.
Dx technically isn't really a number. It's like more of a representation of the variable.
Yeah, dx is not a number. Definitely not a number. It's called in different contexts. Sometimes it's called an infinitesimal or a differential form or something like that. Or sometimes we just say the dx it doesn't really mean anything. It's just an indication that goes along with the integral sign that tells you what the variable is that you're integrating. But it does, at some level, represent derivative of something. It's true that dx is not a number, but whatever dx is, dv is of the same type. So I don't exactly feel nervous writing dv as just dx, even though dx is not a number. I mean, dv is not a number either, so it's not so bad to write. Anyway, what do we get for the rest of it? U is ln x, so du, what's the du going to be? Yeah, it's the derivative, 1 over x, and dx, of course, is always part of the du. And then what about dv equals 1 dx? So v is integral of 1 dx. And what's that? It's just x. Yep. All right. And so we can do the integration by parts formula. uv minus integral v du is, okay, u is ln x, v is x minus integral v is x, du is 1 over x dx. All right. Can we simplify the integral there? I think so. Yeah, x times 1 over x, they cancel, and we just get a 1 inside the integral sign. So this is, I'm going to write it this way around so there's no ambiguity. That second x is not part of the log there. So it's x ln x minus integral of 1 dx. And the integral of 1 dx is, again, x, same as what we said before. So this is x ln x minus x plus c, and that's the answer. All right. So actually, this is a formula that you will typically see, in the back of the book or something, in a big list of integration formulas. This is a true fact. Integral of ln x dx equals x ln x minus x. I don't have this formula memorized. It doesn't come up very often, but it is a true fact about the natural log. It requires integration by parts in order to figure out this formula. All right. Anybody got questions about that one? Great. I had some examples for you all to try. We got 10 minutes left. I think we can do some examples. So how about you try? I got a few here. I got 2. And I'm going to give you some advice for this one. The second one is a quotient, right? The integration by parts is always about a product, something times something else, u times dv. So this one, before you do parts, write it as a product. Similar to, you're not going to use L'Hopital's rule, but we had to do similar things to do L'Hopital's rule, to force the thing to look in the form that we want it to look. In order to do the parts on the second one there, you're going to have to force it to look like a product. And I'm going to also suggest you use this integral formula. Will make things a little easier. E to the x by itself is very easy to work with. Here I wrote e to the 4x. How does that 4 matter at all? Well, it matters in this way. When you take the integral of e to some constant times x, that's what happens to it. All right. I'll give you a few minutes to try these out, and then hopefully we'll have enough time to go over them. I don't know if it's enough time to do both of them.
Genuinely starting to feel less stupid every time I walk in.
Okay. Some people feel the opposite. It's good. You start with the hardest stuff. Folks at home doing all right? Maybe.
Yep.
Okay, good.
Yep, doing good.
All right. All right, we gotta go in a few minutes, so I think we better do these. I know this was not really enough time to do both of them, but let's see what we think. So let's do the x ln x first. This one, we want to choose, in this case, the u you should choose as ln x because that one is going to get nicer after taking the derivative. The du becomes 1 over x dx. That means I must choose dv to be x dx, and unfortunately v will be the integral of x dx, which does get slightly more complicated, but it's going to work out fine. This should be 1/2 x squared. Right, and then when I plug in, I'll do it over here, I go u v minus integral v du, I get ln x is the u, the v is 1/2 x squared, minus integral v du is, come on now, 1/2 x squared times 1 over x dx. I think this is what folks got. Then you can simplify a little bit inside the integral there. Let's pull the 1/2 out and simplify the x's. X squared over x makes x. So this is, I like my things to be in front of the log for some reason. 1/2 integral of x, right? And then that integral of x becomes another 1/2 x squared. So this is 1/2 x squared ln x minus 1/2 times 1/2 x squared. And this is the answer. I hope that's what you got. As I was walking around, it seemed to be this is what people were getting. Any questions about that one? Excellent. You definitely, in this case, you definitely want to choose the u to be the ln x, because if you put ln in the dv, you're going to integrate ln. It's not good. You don't want that. All right, let's do this one. So my advice was write this as a product. I suppose there's the most natural way, in my opinion, to write it as a product is to elevate the denominator and make the exponent negative. So this I would write as integral x times e to the negative 4x. Right? I suppose I don't really know how else you would write this as a product. You know, I guess there are other ways, but they're even more complicated than that. This is the simplest way to write this as a product. All right, and now I'm going to choose my u's and dv's. What did you choose for the u in this one? I know some of you did this one. Yeah, let's choose u to be x, because in the next step I'm going to take the derivative and it will go away. So du is just going to be dx, which I like. The dv then must be the rest of it, so the dv should be e to the minus 4x dx, which means v is the integral e to the minus 4x dx, and I will use my little cute little formula there. It becomes 1 over negative 4 e to the negative 4x. All right, and just because it's time to go, I'll finish this off real quick. It's uv minus integral v du. Notice I put the little tail on the u every time. That's because otherwise it looks like a v. I hope you can keep it straight for yourself. I had to change the font of my handwriting when I became a mathematician. It's true. Life choices. uv is x, and then v is 1 over negative 4 e to the minus 4x. And then I go minus integral v, 1 over negative 4 e to the minus 4x. du is dx. Simplify the integral by pulling out 1 over negative 4. So this becomes negative 1/4 x e to the minus 4x, and then plus 1/4 integral e to the minus 4x dx. And I do the integral again using the same formula that I used before. Minus 1/4 x e to the minus 4x plus 1/4 times minus 1/4 e to the minus 4x. That's the answer. I hope you got something like that. Sorry, I went over by a minute. Oh, I didn't. It says 9:50. All right, that'll do for today. No quiz on Friday because there's no homework due today. So in another time, I would accept. All right, see you all on Friday. Have a good one.
Thank you.
Bye-bye.